Happy Wednesday. I hope you guys are having a good day. Mine's coming along. I snuck out today for a lunch run. It was great. That's a lie. It was super hot. It was so hot outside, but in the grand scheme of things, it wasn't that bad. I had thought I'd finished my coffee. Lols. It says dream big, which reminds me that someday we're going to get to go to stores again, like Target or like, I don't know, nowhere. I can just go somewhere. I can just go anywhere. I can go everywhere. So that always sounds fun. Let's see, other excitement. We have 2 more weeks of class after this. I didn't realize I had forgotten to post the announcement slides for like the last several, but I did. So you can pop in and look at those. Today's announcement slide, the one from lecture 25, has 2 new animals in it. Yeah, but Sarah, today's announcement slide has a dog and a cat. Neither of them are mine. Since your animals. So today we have a cat, Phoebe. Phoebe is named after Phoebe from Friends, and a golden retriever named Harper Grace. Harper Grace and Lily are very good friends. They like to go to the dog park together. They like to get margaritas together, or just, go on long walks or do all of the other normal dog stuff. But we can't see them because no one can go anywhere right now. So their mom sent me a picture. She's super cute. They're like snuggling. It just makes me happy. So Lily is not partaking in class today. I don't know. She like walked out and went to sleep, and I was like, you don't want to come to class? So that's where she is. I'll give it a few more minutes. Let's see. I'm trying to think if I have other things to tell you guys. Not really a whole lot. Like, I went for a run today. It was hot. I didn't like it. I didn't want to be running. I wanted to go lay by the pool, but that's not a choice either. So, I made popcorn as a snack today. I'm also using it as a demo, so we'll see how this works. A couple of things about Zoom. So it's become apparent, so you may have heard about this Zoom bombing thing where people like pop into random Zooms and scream dirty words, say mean things, and then like screencast and show wildly inappropriate things. So the newest update, at least on my end, is starting to create some protections for that. But what it does is it puts you in a waiting room. It's not like it rings a doorbell and I know that you went in the waiting room. You just go in the waiting room and I don't know. So if you end up in the waiting room, send me an email and I will let you in. I'm trying to get better about looking consistently to make sure that you're not like stuck in the middle of nowhere, just waiting for help. Megan might be having the same issues. So there are other ways you can set up Zoom meetings where you don't need a password and you don't go into a waiting room. But right now, my office hours have a waiting room. You go in there, I will let you in. They're still the same as they've always been, kind of a multi-panel screen in Zoom if you want to do that. I may try to hold some extra office hours before the exam next week so that if you have questions while you're studying or trying to look over the material, you can do that. There's something else. I made a note in my planner to open up all of the keys on Sunday sometime so that you can use them for the to keep studying for the worksheet keys. There's a Vesper worksheet, another, like an extra worksheet that opened up yesterday. I hope I unlocked that. I'm looking at Canvas right now to make sure that everything you need to see is available. Right, you're gonna have a meltdown. let's see. On Canvas, there is a new module that is, I don't want to call it important, but kind of exciting. At the very bottom of the modules page, like, I know, scroll, keep scrolling. There's a Vesper handout, which is where the table that I sent you, and then there's a worksheet, which is just more practice. Totally optional. Everything's optional. There are lots of things hidden in there for you in different places. And I think I just realized that I forgot to put the quip online, but I can't tell that. The quip is not yet available. Hold that thought. Y'all. I'm breaking my computer. There you go. If you're looking at the handouts slides, they look a little bit different. We're going to do our absolute best to learn what we need to do. Depending on how far we get, we will get as far as that is. My guess is, so today I want to teach you all of the Vesper, like what the different things are, what they look like, how to draw them. And then you will go ahead and set up. So on Monday, we will do more example problems. We'll talk about a few more different topics. So 9.3, 4, and 5, which are relatively short. We may get to some of that today. 9.6 is an online video that's about 15 minutes. It's the other style of video, not this. I will post the link for you in the announcements. I'll post it in a bunch of places so you can find it. But I think that's a pretty good video for you to watch just to give you some more information. You have Alex due tomorrow, Monday, and Wednesday of next week, because there's always topics due on the exam day. Then there's Open Pi. Then we will have one last set of classes. So Quip 10 opens today at 4:15. It is a different. So last week we tested the quiz version. You guys could upload files. It was really, well, this is not important. It was super difficult for me to grade. So we're going to try a slightly different version of an upload. It should function the exact same on your end. It is going to just tell you it has to be a PDF. So some of you, and I tried to give you some information if I caught it, uploaded JPEGs or PNGs or some other type of digital file. So it needs to be a PDF. It will tell you that. It should allow you to upload more than once if you mess it up. So you can do that. So the Quip opens today. It is on how to draw a Lewis dot structure. And our exam 3 is next week. It will be on Canvas. We will not be using Respondus or lockdown browsers or anything else. For the time limits, there will be some. I'm still trying to make sure that we can do what I need to do before I give you guys too much details. There has to be some version of a time limit. But right now, I can't tell you exactly how it's going to work. There will be more information this week, and I will give you as much information. My goal is to tell you everything you need. Okay. So Open Pi. I'm writing this in the comments so you can look back for it later. So Open Pi is from April 15 to the 20 and April 24 to 27. So Haley asked, the Quip today has to be a PDF. Yes, it will be a file upload, and this one will lock you out of that version. And Angelina is correct that the Notes app will allow you to make a scan and save a PDF file. It should be relatively simple for you to do that. Cam Scanner works perfect. It is what I use when I need to upload pictures. So happy to help in any way I can. If you're having technical difficulties or do not have access to something that will allow you to upload a PDF, please let me know, and I will try to help out in a way that I think we can do that. Otherwise, that's all I got. So if you guys have questions for the announcements, you can drop them in the comments box, and I'll try to look at that. Don't forget that SI is currently happening. There is a session tomorrow. Yeah, it's tomorrow. And then next week, she will have exam review sessions. I think they're in the past when we were face-to-face in person, not face-to-face from my house to your house. Megan's review sessions were on Tuesday and Wednesday. I will likely try to reschedule my Tuesday Zoom out. I'll give you the opportunity to try and meet with both of us if you'd like. Okay. So let's start talking about class. Hold on. So Sarah asks, does this quip have a time limit? So this is a slightly different format. It does not have a time limit. So it is due by 11:59. So you could take a long time to do it. Keep in mind that the exam will have some parts of it, or all of it. I don't know enough, but there will be a time constraint on that one. So Sarah, you will be good to go for the quip today. It is not timed. You should still try to do it by yourself without Google, if at all humanly possible. But you should be able to do that. It should allow you, if you have some type of issues, you should be able to see it. I'm hoping to be able to write on them. So, because that's what we would like to be able to do for the exam. So, good question. All right. Sorry, getting everything situated. Okay, so today we are going to talk about molecular geometry. Now, I for one did not love geometry as a class when I was in school. You know, what feels like 900 years ago. So if you look at slide, awesome, none of these have slide numbers because I forgot. If you look at the outline slides, only 9.1 through 9.6 will be covered. Molecular orbitals and diatomic molecules, we're not covering that this year. So we're going to talk about molecular shapes, Vesper, how do molecules form? So if we think about molecular shape, so 9.1. Sure all this works, yeah. Molecular shape. So the real question is, if we think about a Lewis dot structure. So Lewis dots are pretty simple. So Lewis dots tells us about two-dimensional or connectivity. So if we think about drawing a structure in 2 dimensions, basically on a sheet of paper, whoops, hold up. So one of the issues that we have with that is, what does it really look like in 3D? So if you make a model of my hand and you trace it on a flat piece of paper, it doesn't tell you maybe if I have like big fat hands or skinny hands or anything else. It just tells you that my hand looks like this. If I make my hand look like this, it's a totally different 3-dimensional shape than this, but we're just rearranging how the fingers work. So if we think about carbon tetrachloride, and so if we want to draw a Lewis dot structure of that, it's going to look something like this. Where the only carbon is connected to all of the chlorines. All of the chlorines have 3 lone pairs of electrons and 1 bonding pair. In 9 years, when we finish all of our lone pairs, it looks like this. So the question we have to start, or we want to start to ask ourselves is, what does this look like in 3 dimensions? So if you look at, I think slide 4, hold on, there is an easy way for me to add slides, not you necessarily, but I will repost the slides with slide numbers later because I totally didn't realize they weren't there. So on slide 4, it asks, what does carbon tetrachloride look like in 3 dimensions? So this is a 2-dimensional structure. If we were to have, y'all, I brought props today. So today's props are a gummy chew thing. I eat them when I run, and popcorn on sticks. So if the carbon molecule is our thing in the middle, this looks a lot like our Lewis dot structure. The thing is, as you can see, there's nothing on this side. So they're equally spaced as long as we're only in one plane. But 3D has the whole thing. So is this really the best way to think about this? It turns out that it's not at all close. So we want, all of our atoms want to be as far apart as humanly possible. So Vesper, which is what we're going to talk about, is going to allow us to move our, this is going to like fall apart as soon as I do it. Oh. So now if we have this kind of ugly, not exactly perfect, but acceptable 3D structure, it tells us that all of these are equidistant, equally spaced apart from one another. That is our goal in this day and age. So, hold on. Gotta set those down so we can draw. So carbon tetrachloride looks something like this, with all of its lone pairs hanging out in 3D. Now I'm going to teach you guys how to draw that in 3D, so don't panic just yet. So the goal of Vesper is to determine the arrangement So when we think about Vesper, here's what we want to think about. How does it go from a flat and two-dimensional structure in a Lewis dot to a three-dimensional structure? So the thing that we want to start to think about is, how do we set these up? So the goal is to determine the arrangement that gives atoms and electrons as much space as possible. So the goal here is, I need a new marker, hold up, is for us to be able to determine how far apart they are. So we're going to look at things like bond angles, geometry. And so then we're going to start look at interactions with lone pairs. So what we want to really start to think about today is, what do they look like in three-dimensional space? So we made that model, and is that model only for carbon tetrachloride, Or is that model good for anything that looks kind of like that? And when does it not look like that? So there are a couple of different things that we're going to talk about. So if we now go to the Vesper slide, so it's titled 9.2, it should be slide 5. So in the Vesper model, it's going to give us a 3D shape. So Vesper stands for Valence Shell Electron Repulsion Model. So some people call it VSEPR. In my real Southern way, I just want to make it all one word, so Vesper. You could call it anything you like. I will understand you if you call it VSEPR or Vesper. It's kind of up to you. So Vesper, there are a couple of things that we want to think about. So Vesper is going to give us two different things, or several things. One, it's going to give us the 3D shape. And these 3D shapes, it turns out, are broken up into two different geometries. So now if you look at slide 6, it tells you the electron domain geometry, steric number, and molecular shape. So electron domain this is often also called the base geometry. This is how many things are connected to the central atom, which is another fancy way of saying steric number. So the steric number is, in fact, how many things are connected. For electron domain or the base geometry, there are there are 6, and only 6 options. And so today what we're going to do is we're going to work through all 6 of those options. We're going to start with the most complex and go all the way down to the easiest. I find that that gives you an easier way to think in 3D and then kind of take it back apart as we go back in time. So the electron domain geometry or the base geometry it's basically, here are your 6 options. And then within that, we have something called the molecular shape. So molecular shape is what we can see. So this is a name for the orientation of the molecule. Now, if you, let me grab mine. If you made the table that looks like this, I'm basically telling you what all of the definitions are here, and then we're going to basically go together and fill this out. So when we think about the electron domain, we're going to start with one base and then look at all of the different shapes and then go through all of the other electron domain bases. So the other thing we want to think about on slide 7 are the types of interactions. So as we start to think about this 3-dimensional shape, we have bonding and non-bonding, otherwise known as lone pairs. So if we think about ammonia, which is NH3, we can draw our N in the center. We're going to add all of our atoms. If we made our valence electrons, it's 5 plus 3 times 1, which is 8. So we've used 2, 4, 6. We have 8 here. So when we calculate the steric number on ammonia, the steric number is equal to 4. And we got the steric number of 4 because there are 1, 2, 3 hydrogens, so that gives us 3, and a single lone pair. So this lone pair or non-bonding so when we think about the base geometry, it's how many things are connected to the central atom, in this case nitrogen. So there's 4, something we can see. So when we think about that, so what I was saying before it buffered, for hopefully someone, was that electrons are things that we cannot see. So we can't name it based on what we can't see. So when we name the molecular shape, we're only going to take into account what we can see, which are atoms. So electrons will shape things, but we can't see them. Now, I know that right now it feels like, but Dr. Malcolm, what are you talking about? So it's a fun statement. So what we're going to do next is we're going to start looking at this table. I'm going to start with the one that has total domains or steric numbers of 6. If you downloaded, so in the announcement that I posted kind of not late, but like yesterday evening, I mentioned that if you could only print one thing, this is the thing I would print. So there's this document. So because the board is small, we're going to try to do some things. So Sebastian asked, what is the steric number? To determine the steric number, you count how many things are connected to the central atom. So in nitrogen, there are 3 hydrogens and a single lone pair of electrons, which gives you 4 things. This will make, I don't want to say way more sense, but it will make more sense as we move along. So don't panic just yet. So, there is one other thing we need to talk about. So the way we're going to draw this, so I will write, yes, you will always count the lone pairs connected to the central atom to determine the steric number. So we'll title this, How Do We Draw in 3D? So some of you are really fantastic artists. I myself am a really atrocious artist, and that's okay. But the thing is, we all want to be able to draw something together, and the goal is that if I draw it, somebody else should be able to see that. So geometry is typically only for the central atom, but you can do it for any atom. But to determine the shape, you have to only count the atom of interest. So to draw in 3 dimensions, if we go back to carbon tetrachloride, I drew something like this. Now, a couple of different shapes and visually different things you should think about. So we now have lines, something called a dash, and something called a wedge. So lines are in the plane of the paper. So that means that our model, if we go back to the structure that I made earlier, so in this model, which I know is a little hard to see, but what we can see is that we have these 2, which are in the same plane. So they're the same. So those are going to be the 2 here and here. Then, for better or for worse, if we show it this way, if the plane of the paper is right here, you can see that one of them is in front of my hand. If I move my hand, you can see the one behind. So it turns out that we want to be able to indicate that in 3 dimensions. So a wedge indicates out of the plane. So basically, no one can really see my molecule, so I'll bring it closer to you. So this piece is sticking towards you, and this piece is behind these two. Popcorn probably wasn't my best option. So this back here, these are called dashes. And so dashes and wedges can kind of both come in 2 or 3 different varieties. So I draw mine as a series of the same width lines. You can also make them look like this, or you can make them look like this. So basically you can make them as a wedge out or a wedge in. Mine just look like that. So in this case, your wedges just need to indicate that it's behind. A couple of things here. We're going to do our best to learn bond angles, which I know sound terrifying, but that's okay. This word is out. Or you could also write in front. So dashes are behind the plane. So this is how we're going to indicate these. Now, for the next 45 minutes, hopefully we'll take less than that, but you never know. What we're going to do is to start to think about how do we build these models. So the steric numbers go really from 1 to 6. 1 doesn't really exist, so we're going to start with 6. 6 is the most complex, then we're going to work our way easier. So to draw in 3D, I'm going to attempt to create this table. It is not going to look like your table. Mine's going to be an up and down table, and it's basically going to kind of move around. But we're going to think about what does it mean for the different domains, the electron domains, base geometries, and then the molecular geometry. So our electron / base. Oh man, hold up. We're gonna do this slightly different. For a steric number of 6, our base electron is octahedral. So in general, this is going to be written as A to our central atom X6. So hold on, marker shenanigans. Katie, we are on that worksheet. We're on the first page. We're going to start filling out the boxes as you go across. I'm going to try to write down all of the right things. In my mind, this was going to work slightly differently. So if we have, now we're going to try grape and see if this works better. If we have 6 items, otherwise known as popcorns on a stick, and we want them to all connect to something in the center, we need them to spread out to where they're not all together. So when we think about that, if we have a I'll lose that popcorn here in just a second. Sorry, trying to make sure you guys can still see. Oh, man. Ah! They're all dying, y'all. Getting a little popcorn on my computer. Okay. This was a terrible idea. So what you can kind of see is this kind of looks like a jack. So when you look at this, we can see it looks the same, almost differently on how you look at it. So this is what's called the base geometry is octahedral. Basically, if you stick 6 things into a sphere, we want them to be as far apart as possible. In this case, I'm sorry, my popcorn keeps falling off. I'll make a different plan for Monday. This was what we came up with today. They may all switch to grapes, but not the best. So in this case, we have an octahedral. Now, the way you can draw octahedral, if you draw this, is A is your central atom. Where you have the x's out here. So AX6 means that you have a central A atom. Ooh, raisins. I think I have raisins. It's a great idea. I knew I should have asked you guys. Not gonna lie, we may have to try this on your own and I'm gonna get raisins because popcorn is a terrible plan and grapes are leaking everywhere. So if I had gone to the store, but like, hey, social distancing, I would have bought gumdrops, but no one has gumdrops because they're weird. This is the diagram. So if you are looking at your graphic, this one does not look the same as yours. So in the diagram, this is here. Marshmallows. I don't own those either because they're not very healthy. Next, we're going to talk about bonded atoms and lone pairs. So, nope. Okay, we can see that. So bonded atoms is asking how many molecules are connected. So there are 6 X's connected around this. So the bonded atoms is 6. Now, are there any lone pairs connected to the A? Well, there aren't really any lone pairs in this at all. So this is going to be 0. Now, Sarah, you could make that. It will not work for some of the next ones, but that is an option for this as well. So the base electron geometry is octahedral. So it turns out if we have no lone pairs, the molecular shape, you guys see that? Yeah. Is also going to be octahedral. So when we think about stock structure. One second, Julia. So this angle here is 90 degrees, as are all of these. So in a true octahedral molecule, all of them are 90 degrees. So Julia asks, when I ask for a Lewis dot structure, is it the same as Vesper? Do you always have to ask, do we always have to think about a molecule in 3D, or does the simple Lewis dot structure work? So if I ask for the Lewis dot structure, this is not correct. It will tell you, so today's quip is not about this. It's about the 90-degree angles in between.
So on this graphic, the last 2 lines, there's an example. You'll fill that out as you come up with examples. You don't necessarily need any. The hybridization, you're going to fill that in later. So don't worry about it today. We will talk about that on Monday. So the thing is, once we start making changes to this, what does it look like? So now we have our, we have our base geometry here. Yes, in an octahedral base molecule, all of them are 90 degrees. However, if we go into the next structure, which is AX5E, which means we're going to lose one of these popcorns to become a lone pair. I'm going to pick one at random. Lone pair, there are no lone pairs in this molecule. So you just count them up. I know that it's hard to fill out the table, but it will start to make more sense the further we go into the table. So in this octahedral molecule, one of these is going to become a lone pair. So we're going to move this. Now, my second horizontal grape is going to be my lone pair. Lone pairs are big and they take up too much space. So when we do that, we're going to start to change the dynamics of everyone else. This is so hard to see. I'm really sorry. You basically are going to squish. Yeah, life is hard. So the lone pair is going to squish these away. So for AX5E, we're going to make some changes to the molecule we have. So these are going to go away. We're going to add a single E. I'm going to put it at the bottom. You can put it anywhere you like. So for our new molecule, it still has a steric number of 6. E is a lone pair. So now we have a lone pair here. So when we do that, if we count up our bonded atoms, we now only have 5 connected to A. The lone pairs, now we have 1. So the steric number is still 6 because 5 plus 1 equals 6. So there are still 6 items connected to the A, which is our central atom. So the next thing on our list is the molecular shape. Which in this case is going to be called square pyramid. And when we look at that, these are all going to go to slightly less than 90 degrees. Now, you might be asking, so essentially E is part of the initial 6, but it just becomes a lone pair. That is correct. How on earth are you going to memorize all this? Well, also in that is this graphic here. This, you're responsible for all of this information. You should be able to draw anything like this. So we're going to keep working through these, but this is where if you get lost or anything else, you can look at this table and figure out any of the bond angles or the names. So we have a molecular shape, and here are our bond angles. So the reason the bond angles change is because this lone pair wants to take up more space. Lone pairs are repulsive. Not like they smell bad, but because they are a dense negative charge, basically they want to take up more space. So it's going to push all of these guys just a little up. And a little up isn't necessarily bad. They're just now less than 90. But less than 90 doesn't mean like 65. It means like 88 degrees. So it's just a little movement. Now, the next thing is, what about if we lose unstable connection? So we want our lone pairs to be as far apart as possible, which means that we can't put it on any of these in the plane. We want it to be across from the other one. So we're going to lose that one. On another grape. So now we can start to see that the molecule shape does not have exactly right angles, is going to be quite different than the previous octahedral shape. So let's work on that one. So for AX4E2, we're going to lose a second X to become another electron lone pair. So when we think about the bonded number of atoms, we have 4 and 2 lone pairs that again still total up to 6. But in this case, now our molecule has 4 X's that are all in a plane. What I mean is, based on this molecule, which I know it's kind of a little janky, we can see that all 4 of these popcorns are all in the same plane. They're all pretty level for a given value of Dr. Malcolm used grapes and popcorn. Level. So in this case, the name of this is square planar. And so the bond angles for here are 90 degrees. Now they're 90 degrees because these 2 lone pairs basically can't shove the atoms any more or less than the other ones. So they live in an equatorial plane. Basically, they're just in the middle. So we're going to continue to repeat this process, subbing out one X for an E all the way until we get to A and E, or A and X. So from here, we're going to lose another X, AX3, E3. We're going to change these bond angles. So when we think about this, if we want these, yes, that is correct. The lone pairs here and here basically can't shove anybody else any more than that. So from here, if we want to remove another popcorn, we have to remove any one of these. But it turns out because they're symmetrical, they're all the same. So we're just going to pick off this one. Ooh, this is going to make a mess. And now we have popcorn down, popcorn down. Too bad the dog's not in here to snack on this. So now we have 3, but you can kind of see that they are in this shape, right? So now we're going to lose one of these to make an E. So now we have these 3, although most of the time we tend to draw this slightly differently. So let me find my eraser, and we're going to redraw this to make it look better. So in this case, we have a linear set and a piece right here, and this bond angle is back to slightly less than 90 degrees, but again, very close. So there are 3 bonded atoms, 3 lone pairs, and our molecular shape is actually going to be T-shaped. So what you can see is that every time we remove one, every time an X converts to a set of lone pairs, E4. So now we're going to lose one more. So likely, we want our atoms to be as far apart and our electrons. So we want, it's kind of hard for you guys to see, I know. So we need to remove this one and add on our grape. So now we have basically 4 of these in a plane, and these 2 are as far apart and they're linear. So the bond angle can only be measured between atoms. So electrons, because we can't see them, we can only see their effects. So we can measure where they are in that case. So we have another lone pair here, and this is E. And so in this case, we now have 2 and 4. And these, because the only thing we can see is linear, like 3 points make a line. And so this bond angle is going to be 180 degrees. So for the steric number of 6, those are the base geometries. So you'll notice that this only happens for expanded octets, because we have 2, 4, 6, 8, 10, 12 electrons around our central atom. So not everything can achieve an octahedral state, but many things can. Every time an X. So Angelina, I think what I said is that every time an X converts to a set of lone pairs, we have to rearrange the molecule to where the atoms and the lone pairs are as far apart as humanly possible. So for the linear molecule, it looks like this. So you might ask what happens if we have AX E5. Well, that doesn't exist. There is no way that there's anything else. Yes, this is all of steric number 6. This is all steric number 6, so we're about to go to steric number 5. I'm gonna have a sip of coffee. Whoops, one more thing. The dots by the E's are lone pairs. So when you draw a molecule, would draw lone pairs. However, I'm afraid you aren't able to see the dots. So I will probably do E's and lone pairs from here on out. So for the steric number of 5, our base geometry is going to be something called trigonal, which needs to be spelled right. Trigonal bipyramidal. So we're going to have AX5. So what we want is the ability to create a central atom. I know watching me make molecules is thrilling. Okay, so. So when we create this molecule, we're going to have 2 opposite each other and 3 in a plane, to where we have 5 things connected to our central grape. So when we draw that on the board, we're now going to have to take into account whether they are in the up and down positions or the flat positions. So the base geometry or trigonal bipyramidal looks like this, to where we have 2 in a line and 3 in a plane. So basically, in this case, we're going to have now 2 different bond angles. This bond angle, which is 90 degrees, and this bond angle, which is 120 degrees. So basically it's saying that we have them in a line and then a plane of them as we come across. So the bonded number of atoms in this case is 5. The number of lone pairs is 0. And because the molecular shape doesn't actually have any electrons or lone pairs, it's the same as the base geometry. So in this case, it's trigonal black rainbow. So for this molecule, the question is, now what happens if we start to remove a single atom to create a lone pair, or to convert into a lone pair? So if we go back to our, you're giving it away, Mr. Popcorn. So the question becomes, which of these do we now remove in order to give ourselves the best chance of these to be separate? It turns out that, like the popcorn that just gave up, we're going to remove one of the ones in the plane because that gives everybody else as much space as possible. So now we're going to add a lone pair on to this one. AX4E. So we're going to lose this guy out here, convert it into a lone pair. And so it turns out that now we have 4 bonded atoms and 1 lone pair, and the molecular shape is seesaw. Now, personally, I find it a little difficult to see that, but if you put it this way, you can, oh my gosh, y'all, I hope you're having a good chuckle around here because I'm struggling. Now, we can kind of imagine that this looks like a seesaw, or you can just remember my panicked face that doesn't look like a seesaw, but what ifs. So this is seesaw. And so the trick is, or the other statement is, what are the bond angles? And this is going to be slightly less than 90, and this is going to be slightly less than 120. So it's the same thing. It's going to get a little bit smaller every single time. So now we need to continue down this process. So when we go to AX3E2, we have 3 bonded atoms, 2 lone pairs, and we've got to get rid of another one of these. We want to continue to take them all out of the same plane. So this turns into an E, or a lone pair. So now when we look at this shape, we've lost another one of these. But now these are all at 90-degree angles, give or take. So we have something that looks a lot similar to AX3E3, an octahedral. And in that case, it was named T-shape. And so our bond angles are going to go to approximately 90 degrees here, because these 3 are as far apart as humanly possible. So from here, what we've been able to do is to sequentially remove one at a time. So there's only 1 left for steric number of 5. So we're going to go to AX2E3. And we'll go with 2 bonded atoms and 3 lone pairs. So we're going to lose 1 more atom. So we're going to lose the other one off of our equatorial plane. And so this shape we're going to get linear. So what I said before it glitched out is a lot of times when we have AX2, it's going to be linear. Not always, but many of the times. So now we've worked our way all the way through the steric number of 6 and 5. And so now we're going to get what I would call the much more common steric numbers 4, 3, and 2. Now what you'll also notice is that every steric number has fewer options, meaning if there's only 4 positions for a steric number of 4, you can only remove electrons so many times before you're out. Not out of luck, but you're out of an opportunity. So next we're going to think about a steric number of 3. Nope, 4. So the steric number of 4 is probably a more common entity that we're going to see often. So steric number of 4, this base geometry is tetrahedral. So tetrahedral molecules, we're going to start with AX4. And so we already know how to fill out the bonded atoms and the lone pairs. So the angle for AX2E3 is 180 degrees. Because they're in a straight line, Katie, it's 180 degrees. Good question. I must have erased it before that. So for tetrahedral, we're going to go back to our base geometry. It's going to be the geometry that we learned for carbon tetrachloride a little earlier today. So we're going to have A in the center. And 4 X's spread around. So we have 4, 0. The molecular shape is the same as the base geometry if there are no lone pairs connected to the central atom. So this is going to be tetrahedral. So when we look at this, the other question is, what are these bond angles? And so this bond angle is 109. Now, you may have learned in other chemistry courses or in lab that it's 109.5. It is. We're just using a general rounded value here to kind of see what it looks like in this case. You are responsible for 109. I will accept 109 or 109.5. So for this base geometry, hold on. Let me remake a model. I think those grapes are dead. Okay. So, but what we can see in this modified model is that our popcorn molecules 9.5 degrees apart. We have 2 that are in the plane, 1 pointing towards you and 1 pointing towards me. So this is a tetrahedral molecule. So now we're going to go through the same steps that we have for all of the other steric numbers. So we're going to go where we switch from AX4 to AX3E. We're going to lose our bond angles, change all this and this. So when we lose one of these, if they're all equivalent, it doesn't matter which one we lose. So we're just going to take the one at the top because that's how I like it. That's how I feel today. So we now have a lone pair at the top. This might look something similar to like ammonia, where we have a nitrogen with 3 entities and a lone pair. Here, still a steric number of 4. And our molecular shape so the molecular shape of this is trigonal pyramid. So the reason it is named that is because when you take this away, it kind of looks like a pyramid. So it's a 3-sided pyramid with the bottom, it would sit just like this. And so it turns out that that one lone pair is going to make this angle less than 109. So it just makes it a little bit less because this guy basically just has too much space. He wants to push everything around. So the reason we're going to start to see different deformations here is basically due to the fact that it is a little bit easier to see bigger changes. So for AX3E, we see this. So next, it's a lone pair. This is the wrong marker. So ammonia is 107.3, which is less than 105. So both 107.3 and less than 109 are acceptable. And the umbrella effect is another name for the lone pair effect, where it basically just squishes that. So next we want to think about AX2E2. So now we're going to lose another one. All of these are still quite equivalent, and so we can start to lose another one that looks very similar. Pick on the side to where we have two bonded atoms and two lone pairs, and their molecular shape is going to be bent. So in this case, our lone pair or our bond here is going to be much, much less than 109 or 105. Both are acceptable. So in this case, we are now going to squish them even smaller. So a lot of times people draw this molecule a little bit differently. You can draw them also like this, where the two X's are at the bottom in the plane of the paper, where here we are much, much less than 109. So this is the same as this, it's just rotated slightly differently. So for AX1E3, it's going to be linear, kind of like HCl. So we're not going to draw that one because I want to make sure we get through the trigonal planars. So next, for the steric number of 3, we have AX3. Our base electron is going to be trigonal planar, where we want everyone to be as far apart as humanly possible. So we're going to put our A in the center. We're going to put our X's out here, where they're all as far apart as possible. With 3 things, they don't actually need to go in 3 dimensions, because this is as far apart that they can get. So we're going to have AX3, and it will look so AXE3 looks like HCl, and so it's going to be linear. So trigonal planar, these are not all equivalent, but you can see that they're all in the same plane, and they look like this. So in this case, no lone pairs. So the molecular shape and the electron geometry are going to be the same. So we have trigonal planar. And so there are 3 things bonded to this, and this bond angle is 120 degrees. So I forget what's next on your page. So we can continue to do the same things if we remove to AX2E1. This is going to go to less than 120 degrees. We're going to put a lone pair up here. 2, 1. This will turn to bent. So I moved through this one quickly because in the molecules that look like this for a lot of reasons. So the last steric number we are going to talk about today is a steric number of 2. So when we start to think about this, we're going to look at steric numbers of 2. So if we have AX2, we have a central molecule with 2 things connected to it. The question is, how do we get them as far apart as possible? So if we put A, X, X, these are going to be linear. So the bond angle is going to be 180 degrees and linear. Now, earlier, Katie asked, what about AXE3? So AXE3 can often also fall into this category where it looks like this. And so this molecule is also linear because 2 points make a line. So hopefully what I have shown you is the ability to draw all of these. So for the next couple of minutes, what we're going to do is to think about how to start applying this method. So there are some guidelines. In order to do this, we want to start by 1, draw the Lewis dot structure. 2, count the number of domains around our central atom. 3, determine the base geometry. Using the arrangement of the bonded atoms, determine the molecular geometry. So I taught you all of this so we can start to draw molecules. So if you go to slide 13, which is maybe page 7, it's a list of examples. And so for the next, I don't know, like 90 seconds until we run out of time, I'm going to start working through some of these examples. Over the weekend, you want to be able to become way more familiar with this. So on Monday, we will continue our discussion of how to draw in 3D. But for the next 90 seconds, 3 minutes, give or take, we're going to just practice how to do this for full-fledged molecules. So on the example, we have XEF2 as one of our examples, where xenon is our central atom. So I know that we've talked a lot about how noble gases are not involved. They can be involved in some things. They also can, don't forget, have expanded octets. So the valence electrons are 8 plus 2 times 7, which is 14, gives us 22. So the first thing we want to do is draw a Lewis dot structure. So we have X, E, F, F, 1, 2. We're going to give octet to everybody on the outside. So now we've used 16 of our 22 electrons. So now we're going to go back in and add the other 3 lone pairs to our central atom. So from here, we're going to be able to ask questions. Structure has a steric number of 1, 2, 3, 4, 5. So we know that that base geometry is going to be trigonal biplanar, trigonal bipyramidal, which we drew as something that looks like this. So now we can go ahead and add in our lone pairs. And they must have 3-dimensional shape if they're shown. And these, in my class, you are required to draw lone pairs every time. So for XEF2, the Vesper structure looks like this. So Sebastian asked about the exam. I will provide more information both on Friday and Monday. But you will be required to draw things like this, which is why we're trying to determine the best practice for you to upload it onto Canvas. So we have XEF2. So the next examples are going to be NH3 and SF6. So in all of these, don't forget the central atom will always be underlined. So we'll start with NH3. So for NH3, we have 5 plus 3 times 1 equals 8. So we have ammonia. We're going to connect all of our hydrogens. We're going to add this here. So now we have a structure that looks like this. So the steric number of ammonia is 1, 2, 3, 4. So we know that we're going to have a nitrogen with structures that looks like this. So from here, the quip is on last lecture. It's just on Lewis dot structures, so something like this. So from here, we're going to be able to add in our 3 hydrogens and add in our lone pair. And so in this case, our base is tetrahedral, and our molecular is trigonal, pyramidal, and so you can do this. So Katie, Allie, and Isvari all asked different versions of how do you choose which one the hydrogen or the lone pair can go on. In this case, they're all equivalent, so you can use any one of those. So you could have put the hydrogen at the top and the lone pair anywhere else. I tend to draw mine at the top, but as long as this is your base geometry, they're all going to be the same any way you like to put it. So we are about out of time. I will hang around for just a second to see if anyone has any questions based on what we've learned. There is a new Vesper worksheet where you can practice drawing as many of these as possible. And so you will want to practice that before we get to class on Monday. So, but if you have any questions, I'm happy to answer them. That's correct. You could put the lone pairs on the wedge or anywhere else. They're all going to be the same. But when you put the lone pairs on the wedge, please make sure that they are dots clear enough that I can see them in that case. Any other questions? Otherwise, feel free to pop in office hours this evening or make an appointment. Or I know that Megan will talk about this some more in SI. Miss you guys. Hope you have a great rest of your day. Oh, yes, Kaylee. Quip today, exam next Wednesday. More information on the exam coming on Friday and again on Monday. Great questions, you guys.